That's the last session of the board. So it's almost October now. So winter is approaching. The days are getting shorter. Your daylight is getting shorter. So I've turned on the light just in case. Alright. So we had, from the previous session, we had two arithmetic expressions, a plus a times a, and the second one was in parentheses a plus a times a. And here are two parse trees for those two expressions. Okay. Now remember, for the grammar G4, the start variable was this. EXPR, which is short for expression, an arithmetic expression for the two cases. These are two parse trees corresponding to two strings, terminal strings that belong to your language. That's the language of G4, our fourth example of a grammar, context-free grammar, CFG. All right. So we're trying to derive a string of terminals, a plus a times a, and in parentheses a plus a times a. So how to do that? Well, now we've got how many rules? 1, 2, 3, 4, 5, 6. Now you can't see them. You'll need to go back to the previous session to have the rules. But here's how you derive from the starting variable to your terminal string here. So this process is called parsing, where you start here. So parsing is deriving effectively, right? Because you're deriving this from that, and that's parsing. And the tree, I never figured out why computer science calls these things trees. They should have been called roots. That would have been more logical. So, anyway, we're stuck with it now because hundreds of millions of people use the term tree. Like it's an upside down tree. It starts here at the root node, so to speak, and then grows branches downwards. Alright. Okay, so how to do that? So you can, what's the word? This yields this, okay? And that yields this, and that yields that, and so on. Remember the term yield, okay? So parsing involves a lot of yielding, and so you can go from this start variable to this. This will be your right-hand side of a rule that says exp arrow x plus term. Okay, and then you can expand or rewrite exp by term. So there'll be another rule of the form expr arrow term, and so on. So there'll be a rule term arrow factor, and there'll be another rule factor arrow a, and so on. Okay, or another rule would be term arrow term times factor, and so on. You've got six rules you can use, substitution rules. Okay, and you may ask the question, well, how do you know what to expand and so forth? Well, there's the art, right? Remember, you can sort of work backwards, I suppose. Here's the terminal string that you're trying to derive, right? So you can sort of work backwards. It would help you choose which ones to split up. Now this one works, but you could create a parse tree where you get stuck. It doesn't. You get down halfway or something, and there's no way you'd be able to get to your terminal string. So it's a bit of an art, right? It takes experience and judgment, practice. Okay, as you do this, well, in the exercises, the problem part at the end of chapter 2, you'll get practice how to do this. But you can have problems, right? Now, similar thinking goes into the second parse tree. It's a little more complicated. You can see it's a bit longer. Oh, by the way, the way I've drawn these parse trees is a bit different from Sipser. I found his way of doing things far less clear and quite a strong disagreement with the way he does things. I found this way far clearer, because each step that you go down corresponds to a yielding, right? So I found it much easier to follow than his way. Like he would have. What did he do? I need to look. Like he had this plus. He had this plus here, right down here. So it was confusing where the plus, at what stage in the derivation was the plus generated, substituted. It's on page 105 of your textbook, and I don't know if you can actually see that, but you'll see that the way he draws these parse trees is different from mine. Now, opinions differ, right? Even amongst professors. So I wasn't happy with his way of drawing parse trees, so I did it this way. And then these little dots, that's me. That's just showing you how where these terminals where they came from. They're all obviously the terminal string consists of terminals, but where in the tree, the parse tree, were they generated? So I put these little dots to indicate that this one comes from here, and this plus comes from way up here, and so on. Okay, and this one was so close, didn't bother. All right. So there'll be a substitution rule x arrow term. There'll be a rule term arrow term times factor. Now, choosing choosing which rule to use in an appropriate sequence, that's an art, right? It's not obvious, and as your parse tree gets more complex, the more difficult it is to do. And as a computer needs to do this, especially in compilers, talk about that next square pretty much. It's difficult to be a compiler writer. And we keep talking about compilers. It's because compilers use a lot of this theory, context-free grammars and so forth, in the theory of compilation. So compiler writing theory is an important part of the curriculum for computer scientists. Virtually every computer science department, I suppose, would teach compilers, compiler theory. All right, deriving this gets more complicated and more possibilities of going wrong, branching the wrong way, choosing the wrong substitution rule at a particular point in the parse tree. That happens. You will notice when you start doing the exercises that you'll get stuck, and you'll have to go back and try a different substitution rule at a particular point in your tree as you're parsing. Okay. All right. Now these parsing trees, they tend to get used in the software, the code that a compiler writer creates. Remember again, what is a compiler? It's basically just a translation program. It's much easier for computers